We've already talked about how we use a probability mass function to model the probability associated with a discrete random variable. We'll use a probability density function to model the probability associated with a continuous random variable. So if you remember, we looked at the probability mass function for a die roll, and when we graphed that probability mass function, we showed that the probability associated with rolling a 1, 2, 3, 4, 5, or 6 was always 1 out of 6, or approximately 0.167. And so the sketch of that probability mass function looked like this, where we have a uniform distribution. Because the probability remains uniform, it's always the same. The probability is equal for rolling each of these values when we roll a 6-sided die one time. What we notice here is that if we look at the graph of this probability mass function, we're only defining probabilities for these exact values here, the exact value 1, the exact value 2, the exact value 3, etc. We don't define a probability for 1.5 or 2.5 or any value between 1, 2, 3, 4, 5, and 6. And of course, that's because with the probability mass function, we're dealing with a discrete random variable where we have those discrete countable values and no values in between. Remember that a continuous random variable, in contrast, can be defined for an infinite set of values, not just a discrete set of values like this, 1, 2, 3, 4, 5, 6. In other words, if we were to sketch the graph of a probability density function for a continuous random variable, as opposed to a probability mass function for a discrete random variable, we would use a similar set of axes like this, the horizontal axis x and the vertical axis indicating probability. But the sketch of our probability density function might be a curve that looks something like this. And then what we would do is identify values of x. So maybe this value here, x1, this value here, x2. But in theory, for this continuous random variable, we could define an infinite number of values in between x1 and x2, and we could think about the probability of each of those values. And remember, with a continuous random variable, we can always get more and more granular with these values as long as we continue measuring out to a larger number of decimal places. So really, there are an infinite number of values along this horizontal axis for the continuous random variable, in contrast with this discrete random variable, where we just have this discrete countable value set. So this is the kind of variable, the kind of scenario we're trying to model with a probability function. And in this case, we can say that every continuous random variable, x, has a probability density function, f of x. And what we can say about this probability density function is that the probability that the continuous random variable x takes on some value on the interval a to b is given by this expression over here on the right, where this notation here is called the integral. This is the integral from a to b of the function f of x. This dx notation here is like the other side of the integral notation. The integral and the dx sandwich whatever is between them and tells us to perform a specific operation with this function f of x, which we'll talk about. Notice here also that now that we're switching to a continuous random variable, when we're calculating probability, we have to calculate probability over an interval a to b. Whereas with the discrete random variable, we calculated the probability of a specific value, one value at a time. So here we had the probability of rolling a 1, the probability of rolling a 2, the probability of rolling a 3. When we transition to the continuous random variable and the probability density function, we are no longer going to calculate the probability that x takes on a specific value. And the reason for that is because it's essentially impossible for us to measure the probability that x takes on an exact value when we're dealing with a continuous random variable. So let's say, for instance, that the continuous random variable, that the probability density function associated with this continuous random variable here, we've sketched it, and maybe it models finishing times for a standardized test. Let's say here that this is the mean finishing time for the test, and that mean finishing time, let's say, is 71 minutes, such that, let's say here, this x2 value is a finishing time of, we'll call it 80 minutes. Well, if we want to calculate the probability that a student's finishing time is exactly 71 minutes, that's virtually impossible for us to do because they might finish at 71 minutes and 0.00000001 seconds. In other words, they might be off of 71 minutes by a value of time so small that it's almost immeasurable. And because of that theoretical idea, where it's basically impossible for us to measure that they finished truly at exactly 71 minutes, because remember, we can always divide time into smaller and smaller and smaller slices, we can't really ever say the probability that a student finished at exactly 1 minute. And so, with a continuous random variable and its probability density function, the probability of any specific exact value in the range of the continuous random variable, the probability of any exact value is actually 0. So for a variable like this one, the probability that x is exactly equal to 71 minutes is 0. The probability that x is exactly equal to 80 minutes is also 0. The probability that the variable takes on any specific exact value is always 0 because, in theory, for a continuous random variable, we can't pinpoint exactly 71 minutes. We're always going to be off by some infinitely small fraction of a second. However, we can calculate probability over some interval a to b. For instance, we could think about the probability that the student's finishing time is somewhere between 71 minutes and 80 minutes. And in the same way over here, with the probability mass function for a discrete random variable, the probability of one specific value is given by this column or this bar. With a continuous random variable and the probability density function, the probability that the discrete random variable takes on a value in some interval is given by the area under this probability density curve over that particular interval. So if we're interested here in the probability that the student's finishing time is between 71 and 80 minutes, that probability can be represented by all of the area under this curve over this interval. In other words, if we could geometrically calculate the area under this curve here, we would find some value between 0 and 1, and that value for the area would be equivalent to the probability that the variable takes on some value in that interval. So to summarize here, instead of using a probability mass function to calculate that a discrete random variable takes on an exact value, we'll now use a probability density function to calculate the probability that a continuous random variable takes on some value within a specific interval. Now, when it comes to the probability density function, there are a couple things we need to remember. So it has to be true that the probability density function f, or f of x, is greater than or equal to 0 for all possible values of x that the continuous random variable can take on. So that means for all of the values of x between here and here, under the curve of the probability density function, all of these values of x on this interval have to produce a positive value for f of x. And we can think about this curve here as the graph of f of x, which just means that this curve, if we were to sketch f of x, this curve, the sketch of f of x, has to sit above the horizontal axis anywhere. We can't have any negative values. This curve can't dip below the horizontal axis at any point in this interval. So that's our first requirement. And then our second requirement is that the total area under this curve, when we add it all up, has to be equal to 1. Because remember, our vertical axis here represents probability. So the area under this curve is the total probability for all possible values of our continuous random variable. And probability always has to add to 1, which means that all of the area under this curve has to add to 1. And that's what this means here. This integral notation, and then from negative infinity to positive infinity, just means everywhere under the curve of f of x, to integrate means to find the area under the curve. So the area under the curve f of x, everywhere underneath it, when we add all that together, that has to be equal to 1. So that's our second requirement. So that being said, let's go ahead and look at an example. We'll say here that this function f of x is a probability density function as long as we define it over the interval 0 to 1. So under this definition, before we move forward, we need to check to see that we meet both of these criteria here, that f of x is greater than or equal to 0 for all x, and that the total area under the curve is equal to 1. So there's a couple ways that we can go about this, but one easy way to verify this first criteria is to sketch the graph of f. So if we use a calculator or any computer algebra system, any graphing software to sketch f of x, we see this graph here. We're told that we're only looking at the values of x on the interval 0 to 1. So here this is x equals 0, this is x equals 1. And so we're only interested in this section of the graph between these 2 points. And we can see that everywhere between 0 and 1, the graph here is at or above the horizontal axis. And so we meet this first criteria. If we had been given an interval, for instance, of -1 to +1, we can see that over here between -1 and 0, the graph sits below the horizontal axis, and so we would not meet this first criteria, and we could not call this a probability density function. But because the interval's been limited to 0 to 1, and we can see that the graph is at or above the horizontal axis everywhere in that interval, we meet this first criteria. Now, for the second criteria, in order to figure this out by hand, we're going to need to know how to evaluate integrals, and that only comes up in Calculus 1 or Calculus 2, but that's okay. We don't have to know calculus. We don't have to know how to evaluate an integral, because we can still use calculators or computers to help us verify this fact really quickly. So all we have to do is substitute here for f of x 4x cubed. So this is what we would plug into a computer algebra system, software, a computer, to get this integral evaluated for us. We would say here the integral, and then instead of from -infinity to infinity, in the definition here, the interval's been limited to 0 to 1. So we'll say 0 to 1. And then instead of f of x here, we'll put in 4x cubed, our f of x function, and then dx. Again, we can plug this into any calculator or computer, and it will tell us the value of this integral if we don't know how to do integration. The value of this integral is in fact 1, and so we meet this criteria. If we wanted to evaluate this integral by hand, the way that we would do it is by adding 1 to this exponent here to get x to the 4th instead of x cubed. So we would have x to the 4th, and then we would divide by this new exponent of 4. So when we divide this function by 4, it'll cancel this coefficient of 4, and so the integral of 4x cubed is x to the 4th. And then we would evaluate that result, that integrated result, on the given interval 0 to 1. And when we do, when we evaluate over this interval, we always plug in this upper limit here of 1 first. So we get 1 to the 4. And then we always subtract whatever we get when we plug in this lower limit of integration. So when we plug in 0, we get 0 to the 4th here. And of course, when we evaluate that, we get 1 minus 0, or 1. And so we see that the value of that integral over this interval 0 to 1 is in fact 1. And so we can double check that we do in fact meet this requirement. But again, we don't need to know integration if we haven't taken calculus. We can use a computer to help us calculate any integral, the integral of any function f of x over any interval, just to verify that this is 1, and therefore that we have a probability density function. So once we've verified that we have a probability density function, we can answer probability questions about the continuous random variable, like what is the probability that the continuous random variable x takes on some value between, let's say, 1/2 and 3/4. So looking at this curve here, that's this interval here. This is 1/2, and this is 3/4. So that interval, if we want to calculate that probability, what we're looking for is this area here. Geometrically, this physical area, if we can calculate this area, that will give us the probability that x takes on a value between 1/2 and 3/4. And so here's what that would look like if we actually plugged into this formula here. We would say that the probability that x is between a and b, we said 1/2 and 3/4. So 1/2 less than or equal to x less than or equal to 3/4 is equal to the integral from 1/2 to 3/4 of the function f of x, which we were already told was 4x cubed, and then dx. And again, this is the same thing we just did here. We can use any computer or calculator to help us find this value if we don't know how to integrate, or if we want to integrate. Remember we said that the integral of 4x cubed was x to the 4th. So the integral here is x to the 4th, and then we just evaluate that integral over this interval 1/2 to 3/4. We plug in our upper limit of integration first, 3/4. So we get 3/4 to the 4th power, and then we subtract whatever we get when we plug in our lower limit of integration, which is 1/2. So we get 1/2 to the 4th power. And then if we do this math by hand here, we'll get 3 to the 4 is 81, and 4 to the 4 is 256, minus 1 to the 4 is 1, and 2 to the 4 is 16. If we find a common denominator by multiplying this second fraction by 16/16, then we can call this fraction here 16/256 instead of this. And the result then there is 81 minus 16 is 65. So 65/256, which when we convert to a decimal and round is approximately 25.4%. And so what that tells us then is that the probability that our continuous random variable will have a value between 1/2 and 3/4 is just over 25%, given that this is the probability density function that models our continuous random variable over this interval 0 to 1. So again, the biggest takeaway here is that we use probability mass functions to model discrete random variables, and we calculate probability of exact values. When we have a continuous random variable, we instead use a probability density function, and we only calculate probabilities over intervals. We look for the probability that the continuous random variable falls between a and b, instead of that the random variable takes on a specific value like a or b. And in order to calculate that probability, we first check that we meet these two conditions to verify that we do in fact have a probability density function, and then we calculate this integral in order to find the probability over that interval. If we've taken Calculus 1 and Calculus 2 and we're comfortable with integration, we can of course do that by hand, or if not, no problem at all. We can use any calculator, online calculator, computer algebra system, etc. to calculate this integral for us. The result that we get when we integrate the function f of x over the interval a to b should always be a value between 0 and 1. We might get a fraction, but even if we do, we can convert that to a decimal value. In this case, we got approximately 0.254. We can also convert that to a percentage to say there's an approximately 25.4% chance, or we could just say the probability is about 0.254 and make the conclusion that that is the probability that the continuous random variable takes on a value in the interval that we defined in this particular example, the interval 1/2 to 3/4.